Here we are with the heat transfer homework packet that starts with an article about called Submerged, about potential for a strong storm in New York City, and we'll move into a textbook section on heat transfer, three different types of heat transfer. So let's start here at the top of the article. It's called Submerged. Is it only a matter of time before a nightmare storm strikes New York City? Now, I like to make sure that people take note of the date down here. It is from 2008, so it is, I believe, before Hurricane Sandy hit New York City, so just keep that in mind as you're reading. It is a little bit out of date, but it gives you good information about what happens and what could happen when big storms hit cities, which I feel like can be very relevant in the fall. Okay. Howling winds rushed between New York City skyscrapers, shattering windows and uprooting trees. A 7.6 meter, or 25-foot wall of water sweeps over lower Manhattan, submerging the financial district and popular neighborhoods like Chinatown and Little Italy. Subways fill with seawater. Millions of New Yorkers who evacuated the danger zone can't return to their devastated homes. Is this a script from a disaster movie? No, it's a scenario that experts warn could play out in real life. Hurricanes have hit the Northeast, barely missing the city in the past, and a 2001 report ranked New York the third most vulnerable U.S. city to hurricanes, right behind New Orleans and Miami. New Orleans found out the hard way what can happen when a major hurricane strikes a vulnerable city. In 2005, Hurricane Katrina killed 1,800 people and filled New Orleans with floodwaters, forcing the city's residents to flee their homes and take shelter in public areas like the Astrodome in Houston, Texas. With New York City's population at more than 8 million, 16 times the population of New Orleans, could such a tragedy multiply many times over? Fast track to New York. The reason for concern isn't that the Big Apple is a hurricane hotspot. Atlantic hurricanes form far from New York in the tropics, usually between the months of June and November. Warm water evaporating from the ocean fuels their swirling, high-speed winds. As a hurricane rotates, slow-moving streams of air called trade winds, these are a type of global wind, remember. These trade winds carry it across the ocean. Fortunately, most hurricanes run out of steam without reaching land. Areas in the Caribbean, Gulf of Mexico, and southeastern U.S. are at greatest risk from an Atlantic hurricane hit, since the trade winds push storms in this direction. The trade winds move at only 16 to 24 kilometers, which is about 10 to 15 miles per hour, which gives people in the storm's path time to prepare. But some storms turn north and are swept up by faster winds. Kerry Emanuel, an atmospheric scientist at the Massachusetts Institute of Technology, explains, if you get up in higher latitudes, the winds tend to be much stronger. And so the hurricanes, when they get embedded in those winds, move faster. This means that a hurricane on track for New York could accelerate, forcing city residents to act fast. Accelerating hurricanes will cause watches and warnings to be issued more suddenly, says Gary Conti, warning coordination meteorologist for the National Weather Service's Boston and New York office. So people will certainly have less time to prepare for an approaching hurricane, which is forecast to accelerate here across the northeastern United States. Funnel effect. Usually, such a hurricane wouldn't strike the city directly because land to the south of New York acts as a shield. Most strong storms pass to the east of the city. That's what happened in 1938 when New England's worst recorded hurricane struck. Although this monster storm killed hundreds of people in northeastern United States, its strongest winds missed New York City. But the city's geographical location could also be its downfall. New York City sits on a bight, a curve in the coastline that forms New York Bay. That's something you might want to take a note of if you're taking notes right now. It's like a bold word in the text. When you see something italicized like that and then defined right after, that would be a good thing to take note of. If a hurricane were to strike this spot, the storm surge, water pushed toward the shore by a hurricane, note again, that might be a good thing to take note of, would funnel into the bay, piling it up until it flooded parts of Manhattan. Emanuel explains, for the same storm hitting New York, at least at the right angle, you could get a far bigger storm surge than that storm hitting a straight coastline, because the water has nowhere to escape. That's the nightmare scenario for New York, says Greg Holland, an atmospheric scientist at the National Center for Atmospheric Research. The nightmare has happened before. In 1821, a hurricane swept into the bay. The trapped water rose into a 13-foot storm surge that put lower Manhattan underwater. Back then, not many people lived in the flooded area, but today this region is densely populated and includes miles of subway tunnels. If a stronger hurricane were to strike this spot, Conti says, you could end up with surge values ranging from 20 to 25 plus feet across portions of New York City. This funnel effect is the reason the Big Apple ranks so high on the hurricane risk list. Holland says, in New York, the chances of getting a hurricane are actually fairly remote. But when you do get one, if it's anything like the right track, then the consequences are going to be enormous. Hurricane cycles. There is more bad news. Atlantic hurricanes appear to run in cycles. In the mid-1990s, a new cycle started in which both the number and intensity of hurricanes have increased. Holland says, it's the classic double whammy. Normally, scientists would expect the cycle to run its course and the number of hurricanes to decrease. But climate change could throw a wrench in the cycle as rising sea surface temperatures and shifting wind patterns affect hurricane formation and tracks. Climate change is expected to affect hurricane activity in ways that we're still struggling to grasp, Emanuel says. Some studies predict that the number of hurricanes will drop, but that the storms will become more intense. The chance of the nightmare storm hitting the Big Apple may be small, but city officials are taking it seriously. Even though New Yorkers need not live in fear, experts urge them to have a disaster plan. After all, says Holland, it gets pretty hard to think logically once the winds start howling and the water starts running around your ankles. A little forethought can make a big difference in an emergency. Let's take a look through some of the pictures and commentary on the side. So I'm going to go back up to the top here. This is, if you could read it across, this page would be to the left and this one would be to the right. And so it's a little bit of a timeline here. So you have some historic hurricanes. So in 1938, a monster storm struck the coast of Long Island, which destroyed some homes. If you look here, I believe that is 1944. I'm not sure. It's in between 1930 and 1960, that's for sure. Hurricane Carol hit and the streets flooded Long Island as well. And then in 1960, New Yorkers struggled to remain standing during Hurricane Donna. And then, not too long ago, Hurricane Sandy came through, and much of what we just read about in this article actually happened. The subway tunnels flooded, and electric power place had a fuse and sort of exploded, and that caused great power outages throughout all of New York City. Let's see, taking a look here. Map is kind of hard to see, but the dark color here is the water, okay? And the lighter color, even though there's some dark parts, is meant to be the land. It's not water in the land. So it gives you a sense for how small the land is and how big the water is as well, and how water could easily wash over these islands. So it's good to take a look at these pictures to give yourself some context. This picture is just of storm evacuation from Hurricane Katrina, of the people who took refuge in Houston's Astrodome. Just recently, there was Hurricane Harvey in Houston, and so similar scenes played out there as well. Let's take a look at this. Although hurricanes don't pound the Northeast often, they have hit in the past. This map shows hurricane strikes in the Northeast between 1950 and 2007. Which storm had wind speeds between 154 and 177 kilometers per hour? That's like between 96 and 110 miles per hour. Which hurricane greatly affected both Massachusetts and Maine? It's hard to see with the coloring here, but you can kind of see the storms that have happened over time. So starting at the bottom here, 1976, 1985, they're all hitting. See, here's New York, and so New York City would be right here where those dots are, and Long Island would be coming out. Massachusetts is up here a little bit more. Excuse me. And then this last little part here, preparing for the worst. New York City officials have identified the areas most likely to be threatened by storm surges. A total of 2.3 million people live in these regions. Which areas they would evacuate would depend on the severity of the approaching storm. Officials expect most evacuees would shelter with friends and family. For the rest, they've identified shelters that can hold a total of 600,000 people. Last spring, officials even held a competition in which they challenged architects to create plans for housing displaced residents while ruined neighborhoods are rebuilt. And this here is an entry from that competition. All right, so that's pretty interesting. Just keeping in mind, two of the key things that you learned about in that article were these bold words here, bight, which is a curve in the coastline, and then storm surge, which is really that water that rises up and pushes towards the shore by a hurricane. It's not a tsunami. Storm surge is different. It's all of the water rises, not just one big wave. And then one more important thing was just talking about how climate change is really having an effect here on the severity of hurricanes. All right. Let's transition and take a look at this textbook chapter on the transfer of heat. Again, as always, you really want to take a look at the key concepts, the reading preview. This really shows you the stuff that you need to know after you've read this. I usually skip right over these lab zone discovery activity things. If you ever wanted to do something like that at home, you could always follow the instructions and give it a shot. But we do some pretty cool labs in class that will help you with that. So here are the key concepts you need to know. What are the three forms of heat transfer? So by the end you should be able to name 3 different kinds of heat transfer. In what direction does heat always move? And how are conductors and insulators different? These key terms here are going to help you as you are trying to pick out the most important words that would help you answer these questions. So conduction, convection, radiation, a convection current, a conductor, and an insulator. This just gives you an idea on how you could take notes. So if you're having a hard time taking notes, this gives you a framework to do that in. So you could always make up the same thing on a sheet of paper of your own. You could do the main idea and fill in 3 detail ideas about it. So I usually find the main idea is one of those bold words or a bold sentence in a section, and then the details are the things that support it. All right, let's get started. One more tip, I'm sorry, but usually this first paragraph when you're looking to take notes, if it's telling a story, just like a story to give you context to help you understand a situation, there's typically not something you really need to take notes on, but it's important to read and sort of get yourself in the mindset of what they're trying to help you envision. So, just something to keep in mind. Blacksmithing is hot work. A piece of iron held in the fire of the forge becomes warmer and begins to glow. At the same time, the blacksmith feels hot air rising from the forge, and his face and arms begin to feel warmer. Each of these movements of energy is a transfer of heat. So you have iron held in the fire, the blacksmith feeling the hot air on their face and arms, and there's one other type here, potentially, the touch, if you touch that metal, that would be one more type of transfer of heat. How is heat transferred? There are 3 ways that heat can move. Heat is transferred by conduction, convection, and radiation. The blacksmith experiences all 3. Conduction. In the process of conduction, heat is transferred from one particle of matter to another without the movement of the matter. Think of a metal spoon in a pot of water on an electric stove. The fast-moving particles in the hot electric coil collide with the slow-moving particles in the cool pot. The transfer of heat causes the pot's particles to move faster. Then the pot's particles collide with the water's particles, which in turn collide with the particles in the spoon. As the particles move faster, the metal spoon becomes hotter. If you were to touch the spoon, heat would be transferred to your fingers. Too much heat transferred this way can cause a burn. In Figure 7, heat from the fire is transferred to the stone beneath it. Then it is transferred from the stone to the metal tools. This transfer of heat from fire to the tools is due to conduction. Just trying to find Figure 7 so we can take a look at it. Here it is. Let me see if I can make it bigger. Okay, so they're saying in here there's conduction happening. Fast-moving particles in the fire transfer heat as they collide with slow-moving particles in the stone hearth. Eventually, the heat conducts through the stones to the metal tools. Okay, so they're saying the fire is giving the stones heat, and the stones are giving these tools heat. And because they're touching, that's conduction. Oh, I'm just noticing. This page right here, 184, is the same as this page here, just this is smaller. So, just something to keep in mind as you're taking a look here at this. Okay, excuse me, here we are, convection. If you watch a pot of hot water on a stove, you will see the water moving. This movement transfers heat within the water. In convection, heat is transferred by the movement of currents within a fluid. Important to note is what a fluid is. Fluids are both liquids and gases. Even though when we're talking, maybe a doctor recommends when you're sick that you drink a lot of fluids, you know not to drink air. You're going to drink water or other fluids, other liquids that you want to drink. But when we're talking in science class, fluids mean anything that kind of fills up the shape of the container it's in. So that's a liquid and a gas. When the water at the bottom of the pot is heated, its particles move faster. The particles also move farther apart. As a result, the heated water becomes less dense. You may remember that a less dense fluid will float on top of a denser one. So, the heated water rises. The surrounding cooler water flows into it, fill its place. This flow creates a circular motion known as a convection current. Convection currents can transfer heated air. As the air above the fire in Figure 7 is heated, it becomes less dense and rises up the chimney. When the warm air rises, cool air flows into its place. Let's take a look at the picture again. So they don't show it going up the chimney, but basically you could tell that even just right in front of the fireplace, a convection current could be happening. So when the air around the fire is heated, it becomes less dense than the cooler air nearby. The warm air rises up, and the cool air flows in to take its place. So you get this circular motion happening. Let's move on to radiation. Radiation is the transfer of energy by electromagnetic waves. You can feel the radiation from a fire in a fireplace all the way across the room. Unlike conduction and convection, radiation does not require matter to transfer thermal energy. So it can transfer through space, outer space. All of the sun's energy that reaches Earth travels through millions of kilometers of empty space. You can also check out these reading checkpoints at the bottom here. If you can answer that question, then you understood what you needed to from the section above. So it says, how does radiation transfer thermal energy? Through electromagnetic waves, which are types of energy. Let's take a look at this picture and make sure we understand radiation that's happening here. The fire transforms chemical energy in the wood to electromagnetic energy, which radiates heat across the room. Okay, so the burning of the wood will actually send energy radiation out into the room. So you don't have to touch a fire to feel that it's warm, right? You've probably experienced that, whether it's from a candle or a fireplace or a campfire. All right, let's take a look at this figure 8 here, this bowl of food. The soup's heat is transferred to the bowl, the spoon, and the air. Okay, so there's a lot of different types of heat transfer happening here. Okay, even with just a bowl of soup, the hot soup is touching the spoon, and transfer of heat through touch like that is called conduction. Within the soup, the warmer soup might be rising up, and the cooler soup might be sinking down, and then you would get a convection current. If you put your hand over your soup or on the edges of the bowl right after it came off the stove, you might be able to feel heat even if you weren't touching it. That would be radiation. All right, heat moves one way. This is an important thing to note. If two objects have different temperatures, heat will flow from the warmer object to the colder one. When heat flows into matter, the thermal energy of the matter increases. As the thermal energy increases, the temperature increases. So the more thermal energy, the higher the temperature. At the same time, the temperature of the matter losing the heat decreases. Heat will flow from one object to the other until the two objects have the same temperature. You have probably seen this happen to your food. The bowl of hot soup shown in figure 8, for example, cools to room temperature if you don't eat it quickly. So it's showing that heat always moves from hot to cold, or warmer to colder. What happens when something becomes cold, such as when an ice cream is made? The ingredients used to make it, such as milk and sugar, are not nearly as cold as the finished ice cream. In an ice cream maker, the ingredients are put into a metal can that is packed in ice. You might think that the ice transfers cold to the ingredients in the can, but this is not the case. There is no such thing as coldness. Instead, the ingredients grow colder as thermal energy flows from them into the ice. Heat transfer occurs in only one direction. So can you answer this question? Can heat flow from one object to a warmer object? Think about that. Can it flow from an object that's room temperature to a hotter object? No. Heat always flows from hot to cold. So it would flow from that warmer object into the room temperature object. Oh, I just noticed this. This happens to me all the time. You pull some clothes out of the dryer as soon as they're dry. You grab your shirt without a problem. But when you pull out your jeans or your zip-up hoodie, the metal zipper is too hot to touch. What can you infer about which material in your jeans or your hoodie conducts thermal energy better? Probably the metal zipper, right? Because that is making your hand burn, while the fabric really isn't. So let's learn a little bit more about that. Conductors and insulators. Have you ever stepped from a rug to a tile floor on a cold morning? The tile floor feels colder than the rug. Yet, if you measured their temperatures, they would be the same, room temperature. The difference between them has to do with how materials conduct heat. A material can be either a conductor or an insulator. A conductor transfers thermal energy well. An insulator does not transfer thermal energy well. Conductors. A material that conducts heat well is called a conductor. Metals, such as silver and stainless steel, are good conductors. A metal spoon conducts heat better than a wooden spoon. Some materials are good conductors because of the particles they contain and how those particles are arranged. A good conductor, such as a tile floor, feels cool to the touch because it easily transfers heat away from your skin. Insulators. A material that does not conduct heat well is called an insulator. Wood, wool, straw, and paper are good insulators. So are the gases in the air. Clothes and blankets are insulators that slow the transfer of heat out of your body. A well-insulated building is comfortable inside, whether it is hot or cold outdoors. Insulation prevents heat from entering the building in hot weather and from escaping in cold weather. Much of the heat transfer in a building occurs through the windows. For this reason, insulating windows have two panes of glass with a thin space of air between them. The trapped air does not transfer heat as well. So here's an example, like if you could cut away a window. There would be a sheet of glass and a sheet of glass, but in between there would be some space with air. So, if you were understanding that, you would be able to answer this reading checkpoint question. Is air better as an insulator or as a conductor? Well, if it does not transfer heat well, which it says here, then it is not a conductor, it is an insulator. I know it's not fun to sort of look at these questions at the end, but sometimes, without having to answer them in complete sentences or write them anywhere, maybe just looking at them and seeing, would I be able to answer these, that helps you understand how much you really get the content that you're reading. I hope that this was helpful. As always, if you have any questions, you should definitely reach out to your science teacher. This article, or this homework assignment, has some important stuff in it, and some of it can be tricky to understand, and we get that.